Welcome back to the Deep Dive. Today, we're jumping straight into the fundamentals of computer vision, specifically the core task of image classification.
That's right. Our sources today are really from the foundational courses in deep learning, and our mission is pretty simple. We want to trace the path from the most basic attempts at this all the way to the more sophisticated models that really work.
And get at the why behind the math, not just the what.
Exactly. So let's start with the big problem, the one that stumped researchers for decades. It's called the semantic gap.
Okay, the semantic gap. So when you, our listener, look at a picture of a cat, you see a cat, but what does a computer see?
It sees numbers, just a massive grid of them. An image to a machine is a giant 3D array. You've got height, width, and then 3 color channels, red, green, and blue.
And each point in that grid is a brightness value, right? Something from 0 to 255.
Precisely. So a pretty standard photo of a cat, maybe 248 by 400 pixels. Well, that works out to almost 300,000 numbers.
300,000 numbers. And the job is to somehow boil all of that down into one single word, cat.
And the reason that's so hard is because of what we call the need for invariance.
Meaning the algorithm has to know it's a cat, even if all those numbers change dramatically?
Yes. Think about it. A cat facing you versus a cat facing away, that's viewpoint variation. The pixel values are completely different.
Or a cat in bright sunlight versus one in a dark room, that's illumination variation.
Then there's occlusion. What if you can only see its ears poking out from behind a sofa? Right. Or background clutter? A dog on a green lawn has a totally different pixel signature than the same dog on a gray sidewalk.
The raw numbers are just chaos. They don't correlate with the object itself.
They really don't. And that's why you can't just write rules. You can't code if you see 2 pointy triangles, it's a cat. The only way forward is the data-driven approach. You just give the machine thousands or millions of labeled examples and let it figure out the patterns for itself.
Okay, so if we're going with the data-driven approach, what's the absolute simplest place to start? Like the hello world of image classifiers?
That would have to be the k-nearest neighbor classifier, or KNN. It's so simple it almost doesn't feel like learning. It just remembers everything.
Wait, you're saying its entire training process is just saving the entire training set? If I have 50,000 images, it just stores all 50,000 of them.
That's it. That's the whole training process, which is why it's almost never used in practice, but it's a great baseline. When a new test image comes in, it compares that image pixel by pixel to every single one of those 50,000 images it's stored.
And it finds the closest ones?
It finds the K closest ones, and then those K neighbors get to vote on the label. If K is 1, it's even simpler. It just finds the single most similar image and steals its label.
Okay, so how do we define closest when we're talking about, hundreds of thousands of numbers?
We use a distance metric. The two most common are L1 and L2 distance. L1, or Manhattan distance, is the easy one. You just sum up the absolute differences between every corresponding pixel.
So every pixel difference contributes equally. It's a linear cost.
Exactly. Now, L2 distance, or Euclidean distance, is a bit different. You take those differences, you square them, sum them all up, and then take the square root.
Ah, and squaring the differences is the key. So if one pixel is wildly different, L2 is going to penalize that way more than L1 would.
That's the intuition. L2 is often called more unforgiving. It would rather have a bunch of small, medium disagreements across the image than one single glaring error.
All right, but let's talk performance, because this is where the whole idea just falls apart.
It completely falls apart. On a data set like CIFAR-10, you're looking at maybe 38% accuracy, random guessing is 10%, and a good modern network is over 95%, so it's weak.
But the real killer is the speed.
Oh, the speed is the killer. The computation is completely backward. Training is instant. We call that O1 time. You just store the data.
But then prediction, test time.
Test time is a nightmare. It's ON, where N is the size of your training set. So every new image you want to classify requires a full pass through your entire database.
So if my data set doubles, my wait time for an answer doubles. In a real-world app, it's a non-starter.
It's completely untenable. And on top of that, it fails semantically.
Right, because if you have a frog on a white background and a car on a white background,
the algorithm might think they're close because the vast majority of pixels, the white background, are identical. It's matching backgrounds, not objects. It tells you that raw pixel distance is the wrong tool for measuring semantic similarity.
Okay, so before we even try to build a better model, we need to talk about how we test them. We have to choose things like the value of K or the distance metric L1 or L2. These are hyperparameters.
Yes, and this brings us to Probably the single most important rule in all of machine learning.
Which is?
You never, ever, ever tune your hyperparameters on the test set.
Okay, but I'm going to push back. Why not? If I use the test set, I can find the perfect value of k that gives me the highest possible score on that set. Isn't that what I want?
It sounds like what you want, but that score would be a lie. You'd just be overfitting to the specific quirks of that one test set. It's like you're tuning your model to pass one specific exam. The moment you give it a different exam, a new, unseen image from the real world, its performance will be worse than you thought.
Because your reported score is now artificially inflated, you've peeked at the answers.
You have peeked at the answers. So the test set has to be a precious resource. You lock it in a vault and only use it once at the very end for your final report card.
So what's the solution? How do we tune k?
We split the data. You take your big pile of training data and you carve off a small chunk, say 10 or 20%, and you call that your validation set.
A fake test set.
A safe fake test set. You train on the main chunk and you try out all your different values for k on the validation set. Whichever one does best there, that's the one you pick.
And this helps you find that sweet spot, right? Because if k is too low, like k1...
You get really sensitive to noise, you're overfitting, your decision boundary becomes all jagged and unstable.
But if k is too high...
You start blurring everything together. You're underfitting. You lose the ability to see the fine details between classes. The validation set is how you find that balance.
And for small data sets, there's cross-validation, where you rotate which part of the data is the validation set and average the results.
Exactly. It's more computationally expensive, which is why in deep learning with huge data sets, people often just stick with a single validation split. But it gives you a much more robust estimate of performance.
Okay, so we've established KNN is slow, memory-hungry, and semantically broken. We need a totally new approach.
We do. We need to move from a non-parametric model to a parametric one. The goal is to learn a set of parameters from the data, and then you can throw the training data away.
Now, that sounds useful. What does that look like?
It looks like the linear classifier. The idea is beautifully simple. We want one function that takes the image pixels as input and maps them directly to a score for every single class.
And that function is just a linear equation, w times x plus b?
That's our score function. Factoro WB WI plus BB. The image pixels, 6 to $0, get flattened into one long column vector. W is our weight matrix, B is a bias vector.
And the output is just a list of scores. For CFAR 10, it would be 10 scores, one for cat, one for dog, and so on.
Exactly. And the beauty is the efficiency. Once you've gone through the hard work of learning the best W and B, you can completely discard all 50,000 training images. Prediction is just a single, super fast matrix multiplication.
But hold on, doesn't throwing the data away hurt you? I mean, with KNN, you remembered every single example. With a linear classifier, if you never saw a car that was, I don't know, purple, how can it ever classify one?
That's a fantastic question, and it gets right to the heart of generalization. We're not memorizing pixels anymore. We are learning patterns and storing those patterns in the weight matrix W.
The rules.
The rules, exactly. A well-trained W doesn't store examples. It stores a generalized idea of what a car looks like.
So what do these learned rules or patterns in W actually look like?
You can actually visualize them. If you take one row of the W matrix, say the row corresponding to the ship class, and you reshape it back into an image, you get a kind of a learned template.
A prototype for what a ship looks like.
Yes, it's like a ghostly image. You might see that the ship template has learned to put positive weights on blue pixels because ships are often on water. The score for a new image is basically how well it matches this template.
Which brings us back to that two-headed horse problem you mentioned. This is the big limitation of a linear classifier, right?
It is the major limitation. If your data set has horses facing left and horses facing right, the linear classifier is forced to learn only one template for horse, so it averages them together. The template literally looks like a blurry horse with two heads.
It can't handle that kind of variation within a class.
Not with a single template, no. It foreshadows why we'll eventually need something more powerful, like multiple layers.
Okay, so we have our scoring function. Now we need a way to tell the model if its scores are good or bad. We need to quantify our unhappiness.
We need a loss function. This is the objective. We want to find the W and B that make the value of this loss function as small as possible.
Let's start with the SVM, the multi-class support vector machine loss.
The SVM is, you can call it a minimalist. It has one simple demand. It wants the score of the correct class to be higher than the score of every incorrect class by at least a certain fixed margin. We usually just set that margin, delta, to 1.
This is not enough to win. You have to win by a certain amount, a safety buffer.
A safety buffer, exactly. And here's the key part. If the score for the correct class is higher than an incorrect one by more than that margin, the SVM says, great, I'm happy. The loss for that comparison is 0.
It stops caring.
It completely stops caring.
Right.
It only adds to the loss if an incorrect class's score gets inside that safety buffer. It's a very local objective.
But there's another piece to the loss, right? The regularization penalty. Why do we need that?
This is crucial. It's because of the non-uniqueness problem. Imagine you find a weight matrix W that gives you 0 loss. Well, then 2 times W would also give you 0 loss, because all the scores are just scaled up, but their relative differences are the same.
So there could be infinite solutions.
Infinite solutions. We need to add a term that expresses a preference for a certain kind of W. And the most common one is L2 regularization, which is just the sum of all the squared values in W.
And why do we prefer that? What does penalizing large weights do for us?
It encourages the model to use smaller, more diffuse weights. It forces the classifier to pay a little bit of attention to all the pixels rather than putting all its faith in just a few potentially noisy pixels. It's our best defense against overfitting, and it dramatically improves generalization.
Okay, so that's the SVM. What's the alternative?
The alternative is the Softmax classifier, which uses cross-entropy loss, and it has a totally different philosophy. The Softmax classifier doesn't think of the outputs as just scores. It interprets them as unnormalized log probabilities. The Softmax function itself is this beautiful little piece of math that takes those raw scores and squashes them into a proper probability distribution.
So numbers between 0 and 1 that all add up to 1.
Exactly. So your output becomes immediately interpretable. You can say the model thinks there's an 85% chance this is a cat, a 10% chance it's a dog, and a 5% chance it's a car.
I see. And the loss function then tries to make the probability for the correct class as high as possible.
It wants it to be 100%. Or, well, 1.0. It's never truly satisfied until the probability of the correct class is 1 and all others are 0.
So this is the big difference in their personalities. The SVM is happy once it's winning by the margin.
The SVM is a local objective. It's done. A score of 10, 8, 7, and a score of 10, -100, -200 are the same to the SVM. They both have 0 loss if 10 is the correct class.
But the Softmax is a perfectionist.
It is never fully happy. It will always see a tiny bit of loss. It can reduce by pushing that 85% probability up to 86% and then to 87%. It's an aspirational goal, always pushing for more confidence.
And in practice, does one beat the other?
You know, it's interesting. Despite these very different mathematical objectives, in practice, once you tune them well, their performance is usually very comparable.
So let's recap where we are. We started with KNN, which was just raw pixel comparisons. It was slow, memory intensive, and just didn't get the semantics right.
A dead end, really.
Then we jumped to a linear classifier, a huge leap. It's fast, it learns a set of parameters, and we can use these powerful loss functions like SVM or Softmax to find the best possible parameters.
We've built the essential foundation, we have a score function, and we have an objective to optimize. But as we said, the model itself, that single linear template, is still too simple. It's trying to cram all the different ways a car can look into one blurry, averaged-out prototype.
Which leads us to the final provocative thought we want to leave you with. We've built these simple templates. How do we move beyond them? How do we take this basic idea and stack them, build them into hierarchies, where maybe one layer of the model learns to detect simple things, like edges and colors, and the next layer learns to combine those edges into more complex shapes, like eyes or wheels or ears, and a final layer combines those to make a decision.
That ability to go from a single flat template to a deep hierarchical set of feature detectors, that is the transformation from a linear classifier to a neural network, and that really is the heart of deep learning.